Welcome back to Boiler Wild. Another day, another dollar. This is episode 24, and we are going to talk about Steam, the all-powerful Steam. First of all, my name is Eric Johnson, your host, the one, the only, and I am the founder and CEO of Boilearn. We are a training company, help contractors and users learn about boilers, and we have some online classes. We do in-person classes, and growing that. But this podcast is about education about boiler industry topics as well as personal development. Big believer in personal development, and if you want to grow in your career, you have to grow personally and develop personal skills, leadership skills, even if you are not in a leadership position. So Boiler Wild. WILD is an acronym. It stands for work hard, invest in yourself, lead others, and develop yourself into a person of excellence. You should always strive to be better. I strive to be better every day. There's some days I don't, but you want to have more good days where you're pushing forward than days where you're going backwards. So it's enough of that. Actually, one thing, housekeeping. We got the first comment on Spotify, and I appreciate that. On Spotify, we got 5-star reviews. So keep those reviews coming. That is always appreciative. But we have a comment from Kyle Gradowski. Good stuff, Eric. Looking forward to going through the episodes. So I appreciate the comment. If you haven't already, please rate the podcast 5 stars. That helps me out. It takes 30 seconds. It's free. Doesn't cost you anything, but it helps me and lets me know that people find value and are listening. So, Steam. What is Steam? And let's get into a little bit of the specifics of what steam and temperature have to do, or what steam pressure and temperature have to do with each other, and the difference between low pressure steam, high pressure steam, and how pipes are sized. So first of all, if you're not aware, steam is hot, and hot is relative. But steam has a pressure and temperature relationship that is physics, basically. And that is one of the reasons why it is so widely used, because engineers can calculate if we have this pressure steam, it will be this temperature, which is extremely reliable. So there are steam charts and steam tables where you can look up the temperature of steam versus the pressure. And if you are in the steam space, you should already have one of these charts. A lot of times you can just look them up online. Google will tell you, if you just ask it, what is the steam temperature for the pressure? But somebody who is designing a steam system or designing a process will have a specific temperature in mind if they need the temperature. If they're using steam for pressure, then they'll have to have a certain pressure to move an object or something. But a lot of processes are using steam for the temperature. So steam is 212 degrees at 0 psi, which requires 970 BTUs of latent heat. So I talked about it on a previous episode, but there is such thing as sensible heat and latent heat. Sensible heat is what you can measure with the temperature of a thermometer. So if you have water and you have 180 degree water and you raise it to 185 degrees, you are adding sensible heat to the water. Latent heat, which is part of the magic of steam, is heat added in a phase change. It's heat added or heat removed in a phase change. So in order to take water from a liquid to a gas, so the gas would be steam, you have to add latent heat. So there is a poster out there that is the biggest lie. And so I have it pulled up, and it reads, at 211 degrees, water is hot. At 212 degrees, it boils. And with boiling water comes steam. And with steam, you can power a train. 1 extra degree makes all the difference. So that's actually false. So going back to sensible and latent heat, if we have water at 210 degrees, and we keep adding a BTUs to it, we can increase keep adding sensible heat to it, and it becomes 211 degrees. And now we keep adding sensible heat to it, and it becomes 212 degrees. The second, you got to think about it. So a lot of people don't think in absolutes. Physics is very absolute. It's either this or it's that. So the question is, does water turn to steam at 212 degrees? And most people would say yes. And they've all learned that, water boils at 212 degrees. But that is false. Water you cannot turn a liquid to a gas, the water to the steam, at 212 degrees. So when it goes from 211 to 212, all we've added is sensible heat to it. What actually makes it boil and turn to steam is you have to keep adding heat to the water, and that requires 970 BTUs per pound, and that becomes latent heat when we have that phase change. So if you were to measure your water on your stove, you would find that at a certain point, and it kind of happens kind of quickly, so it's hard to measure, and also water does not heat evenly. It will have turbulence, so if you're heating water on the bottom, just like you would on a stove, the hottest part is on the bottom, as that's where the heat from the pot is getting transferred to the water. So if you put your thermometer on the top of the water, and say you have like 6 inches of water in the pot that you're heating, the water is going to be cooler on the top than it is on the bottom. And you're going to see bubbles start to develop on the bottom of the pot. And that will increase as you keep heating the water. And that's eventually the steam bubbles that you are making and then boiling the water from. So same thing happens in a boiler. There's turbulence of the water and flow of the water, and it ends up being the cooler water will drop in the boiler and the warmer water will rise in the boiler, and it turns the water over, and there's currents, and boiler engineers will figure all that out and they'll take that into account. But water doesn't just stay stationary as it's heated. Warm water rises, cool water falls, and it ends up being currents. But going back to the temperature, if you were to measure the pot of the water, you would find that you can have water at 212 degrees and it's not boiling. You have to keep adding heat to it, which is 970 BTUs per pound of water, in order to make it turn to steam. And that's where the lie comes in. So it is possible to have water at 212 degrees. I will also note that whenever we talk about water boiling at 212 degrees, that is at atmospheric pressure at sea level. And as we rise in sea level, so think about like Denver, Colorado, or like, the Rocky Mountains, you are increasing the height above sea level, and you are now reducing your atmospheric pressure, and the water will boil at a lower temperature. So I just want to note that, but that's the difference there is the water boils at a lower temperature. So going back to a steam table and we're talking gauge pressure here. There's a difference between gauge pressure and absolute pressure. That's a story for another day, but gauge pressure on this steam table, we are going by fractions of gauge pressure. So at 1.3 gauge pressure, the steam temperature is 216. At 10.3 gauge pressure, we are at 240 degrees. At 100 psi of gauge, we are at 337. 250 psi, we're at 406, and this is in Fahrenheit. So at 250 psi, 406 Fahrenheit. So that's the temperature. And you have the equivalent latent heat per BTUs a pound of 820 at 250 psi of steam. Now, if we go back to, say, 10 psi of steam, we have a temperature of 240 degrees, and we have a latent heat per BTU per pound of steam at 952. So that's important to understand that as we increase steam pressure, the latent heat BTU per pound decreases. So essentially, if you can run a lower steam pressure, it is more efficient because the latent heat per BTU per pound is greater, which can kind of seem backwards to people. It is also more efficient because you now have to heat the water less. So you will use less fuel for a lower steam pressure on a boiler. So have a scenario. So if we have a high pressure steam boiler, and if you're not aware, high pressure steam starts at anything above 15 psi. So 15.1 technically psi. So low pressure steam is 15 psi and less. High pressure steam is 15.1 and more. Say we have a boiler that runs at 100 psi, and somebody says, "Hey, why are you running at 100 psi?" And they go, "I don't know. We've always ran at 100 psi." So there's two things you can do. If nobody knows why you run at 100 psi, you could hire an engineering firm and you could have them look at the steam system and spend 30 grand on them to figure out why you run at 100 psi, which is fine. Or you could lower it to 95 psi and see if anybody complains. And then you could keep lowering it to 90 psi and see if anybody complains. Wait a couple weeks, lower it to 85 psi, lower it to 80. And this lowering of the steam pressure can actually save you money because now you have to heat the water less, you will use less fuel, and you'll have more BTUs per pound of latent heat in your steam as you lower the pressure. However, you can start having problems if your distribution system is not sized for the pressure. So a lot of times people will think more is better. More of everything is better, right? But unless it's money, that's not always true. So more steam pressure does not equal better. So let's go back to a low pressure steam system. So low pressure steam, typically used for heating, but it can also be used for process. Breweries will, they can use low pressure steam, say 8 psi to heat their kettles to make beer. But low pressure steam, most buildings are designed to run at like 2 psi. And if somebody comes in and says, oh, you're only running at 2 psi and it's not working, well, let me turn that up to 10 psi. More is better, right? The higher pressure needs to push the steam through the pipes. And that is actually false. And why that is lower pressure steam travels at a faster velocity than higher pressure steam, and higher pressure steam takes up less space than lower pressure steam. So on a low pressure steam boiler, you will notice that the steam piping is a larger size than a high pressure steam boiler of the same volume. So you can have a low pressure steam boiler that's, say, like 1 million BTUs per hour of input, and the steam piping will be like 4-inch. You're like, wow, that's some big piping for a low pressure steam. But then you'll get a high pressure steam boiler that's small, same thing, 1 million BTUs per hour, and it can be 1-inch outlet or 1.5 inches. And you're like, man, I would think that a higher pressure steam boiler requires a larger outlet, but it is the opposite. High pressure steam fits into a smaller area, so you can use smaller pipes, and it has less velocity as well. So where this will screw you up is if you have a boiler that is running at, say, 40 psi, and you want to lower the steam pressure because you don't know why we're at 40 psi, and you lower the steam pressure to 20 psi. Well, now the velocity of the steam is faster than if you were at 40 psi. And what can happen is if your exit piping of your boiler, so some people call it like the steam nozzle, but if your exit piping of the boiler, your near piping of the boiler, and your header piping is not sized correctly, you can actually start having water level issues and steam quality issues because now you have higher velocities of your steam because you are lowering the pressure, and that can entrain water in the steam. It can also cause surging and foaming in your boiler, which will also entrain water in the steam, and water will get picked up as the steam leaves the boiler, and now you have excess water inside your steam header. Your traps get overloaded. You can have water hammer issues. You can have steam quality issues. Wet steam will not be as hot. You'll condense faster, and it overall will negatively affect your system. So if you really do want to lower your steam pressure of your boiler and your steam piping is not sized correctly, you actually have to increase the size of your steam piping, and you also have to increase the size of your actual nozzle connection on your boiler. So, for example, we have a fire tube boiler and the boiler was built for a MAWP of 150 psi, and it was ordered many centuries ago or whatever, and you now bought it used, and the boiler shows up on a trailer. You're like, great, this is perfect. This boiler has an MAWP of 150, but we're only going to run it at 40 psi, and everything will be fine. Well, so the exit, the nozzle, the actual like flanged connection on the boiler, say is 2-inch. And what you're not taking into account is that 2-inch, that connection is probably not going to be big enough that you can go. There's engineering in this, but I'm just going to say for 40 psi, it's not big enough because the boiler was actually designed originally for the load and output to say run at 120 psi. So you install it and you start having water level issues, and you get wet steam and you get water in your header. And what is happening is the nozzle on your boiler is too small. And when you are lowering the steam pressure, so you're only running at 40 psi, you now have higher exit velocities. And when you have a small nozzle, that will make the water level in your boiler go wild, and you'll have surging and foaming and all kinds of stuff will happen, which is not good. And the only way to fix that is to increase the steam pressure. And you're like, well, we don't actually need more than 40 psi. Why would we increase the steam pressure? Well, unless you want to pay, and I don't even know if that's possible, but unless you want to pay for somebody to increase the nozzle size of your boiler, so say to like 4-inch, and install the proper piping so that you have the proper velocities, exit velocities of your boiler to keep the water level stable. Unless you want to do that, you have to increase the pressure of your boiler, and then you can use a pressure reducing valve to lower the steam pressure where you need it. The problem with this is you're now paying extra money for extra fuel to make a higher steam pressure than what you need. So it would have been better just to start with a properly sized boiler with a properly sized steam nozzle. Now, I may be wrong on this, so correct me, DM me on LinkedIn or email me. But I think the only downside of having too large of a nozzle is it just costs more, too large of piping. So if you order a boiler and you're running at 100 psi steam pressure, planned steam pressure, and you have a 4-inch nozzle and could get away with a 2-inch nozzle, paying for a 4-inch nozzle and 4-inch piping, I believe there's no downside to that. However, you do want a pressure drop across your non-return valve, and there is a pressure drop needed as you don't want your non-return valve wearing out. But other than that, I think the only downside is you're just paying for larger piping and installation costs. But if that's wrong, tell me. Once again, I'm not a know-it-all. I know enough about boilers and steam that I'm dangerous, but I definitely don't know everything, and I'm not an engineer. Just trying to help educate you and help you learn, help you think about something. So how do we tie this into the real world? So I was a part of a project where the customer had it was a manufacturing facility, and they bought some boilers a long time ago, and in order to save money, they were reducing the pressure that they were actually running. So the boilers were, I don't know, had an MAWP of, I think, 150, but they were only running the boilers at 60 to 70 psi, but they kept lowering the pressure that the boilers were running at because they determined that with their manufacturing process they only needed 30 psi, and they would lower the pressure, but then the water level would start bouncing and they were getting really wet steam, and they would get water hammer in their header. And I told them, you have to actually increase your PSI of steam back to where it was 80 PSI. And unless you want to change up your nozzle size of your boilers, where you have to increase your header piping and the exit piping of your boiler on your steam system. So what they ended up doing eventually was they got a boiler with a larger nozzle size, and then they paid to increase the near boiler piping of the steam system, and they increased the size of it. So it was like 2-inch piping or whatever. They went to 4 or 6-inch, I believe, and the header ended up being, I think, 8-inch, and then they lowered the steam pressure. And now that they could run 30 psi and still maintain the steam quality and maintain a good water level in the boiler without the exit velocity of the steam being too high, which will pick up the water and have entrained water in the boiler. So it required a investment of having the proper size nozzle of your boiler, and also they had to repipe the near piping in the boiler room for the steam system. But now they can, there's a long-term value to it, so now they can run a lower steam pressure and save money. But that is what they wanted to originally do, but it's not as easy as, oh, we'll just lower the pressure. We don't need to run at a higher pressure. If your steam system is not designed for that, for your lower pressure, the increased velocity of your steam, which happens at a lower pressure, will screw up your steam quality and the water level in your boiler. So that is important to remember. It is also important to remember that as you increase in steam pressure, your steam temperature goes up, but your latent heat per pound of steam, BTUs per pound, will decrease. And your total heat will increase. So total heat is your sensible plus latent heat. But that's a lot of engineering. If you are not involved on the engineering side, if you are a service technician, operator, the key takeaways are lowering steam pressure does not lower your velocity. It actually increases your velocity, and that can screw up your water level in your boiler and your steam quality. So you have to keep that in mind. But I have seen central plants or manufacturing facilities where nobody knows why they run 120 psi, and they're like, well, why can't we run 110? And say the boiler rooms and the facility's been around for 60 years. All it takes is some operator to come in for 20 years and increase the pressure by 20 psi, and this is our new pressure we're running at. Nobody checks it. All of a sudden, over the course of 60 years, they're now running at 50 psi higher than what they were originally running at. But nobody's been around from when they started, and nobody wants to do, the calculations of it. So if they were running at 120 psi, it's like, well, why can't we lower the steam pressure? Lower it by 10 psi or even 5 psi if you want to be safer. But if we went from 120 psi to 110, you are now increasing your fuel savings of your boiler, but you may already be running too high of a steam pressure, and it was artificially increased by somebody unnecessarily. But that is the easiest way to decrease your steam pressure, is to just lower it by 5 psi and see if anybody says anything. If you want to do it correctly, you need to hire an engineering firm. They need to look at the size of your piping and your process and all that stuff. But I have seen a lot of facilities where nobody knows why they run at the pressure they run at, and lowering your steam pressure by 10 psi can save you money, and you may be running at a higher pressure than what you really need. So that is a reason to lower your steam pressure. But also, if you lower it too much, one, if your process could be affected, but two, you can now have velocity and steam quality issues. So hopefully I presented that correctly. Once again, I am not an expert. I am not an engineer, and I have a general understanding of steam and how it works, but definitely not strong on the numbers. But if you are not strong on the numbers, don't feel like you have to be strong on the numbers, as long as you generally understand how a steam system works and what happens when you increase pressure, decrease pressure. You can get by, and sometimes that's good enough. Don't feel like you have to be an expert and an engineer. There's a time and place for somebody to crunch numbers, but for a service technician, for example, you go into a place and they say, hey, like, we lowered our steam pressure, or they wouldn't even say that. They say, hey, our water level is wild. We can't keep water in the boiler. All of a sudden the boiler will be running, and all of a sudden the water level just drops out of the sight glass and the boiler shuts off on low water. And if you ask enough questions, they'll say like, oh, like, yeah, we lowered our steam pressure by 30 psi because our plant manager told us to. So you can actually do a calculation. There's calculators online, but you can do a calculation of the exit velocity of the boiler for the pressure and the piping size. You'll have a nozzle size, which was what's welded, or the thread outlet of the boiler, and then you'll have the piping that's actually connected to that. So a lot of times you'll have say a 6-inch nozzle on a boiler, but you'll only have a 4-inch pipe connected to that, and that will be due to back pressure on the boiler. But that's all about the velocity of your steam leaving the boiler, and paying for larger piping is not always what people want to do. But if you ask enough questions, they've lowered the steam pressure, but now lowering steam pressure increases the velocity. Low pressure steam has a higher velocity than high pressure steam, with all things being the same. By lowering the steam pressure of your boiler, you can now have water level issues, and water will get sucked out of the boiler, and surging, foaming can happen when you lower that steam pressure. So actually increasing the steam pressure can stabilize the water level of your boiler, and you actually have to, look at the header piping and the boiler nozzle size in order to actually lower the steam pressure of your boiler. It's not as easy as just turning down your pressure control. of, yep, we're going to run 30 psi lower now, and everything's going to be fine. If you cross that mark of having too high a velocity in your piping, you'll have water level, steam quality issues, water in your header. You'll probably overload your traps because now you have more water than what they're designed for. Their traps are only designed for the condensate, that is, steam going from a gas and condensing into condensate, which is water. If you're artificially just picking up water out of your boiler and slugging it into your header, you're probably going to have water slugging around in your header as your traps try to deal with all that extra water that they're not designed to have. But that's a scenario that you can come across. But as a service technician, you can look up a calculator for exit velocities, and it'll tell you, for a boiler, 5,000 feet per minute. I believe it's 5,000, but there's so many feet per minute of steam that's recommended. And if you go over, it's going to be too high and whatnot. So that you don't have to know the exact engineering of it. You just have to be able to spot the problem. And hopefully spotting the problem is 90% of it. And that's where, if you're not the engineer and you have an engineer in your company or somebody who's more knowledgeable, you can call them, hey, this is the problem. This is what they did. I don't know the exact reason or like what the exact fix is. And can you help me with this? And they can, walk you through the numbers or do the calculation. Hey, it actually needs to be this. And, if you increase the steam pressure by 20 PSI instead of 30 PSI, they should have a, fix or get by. So you increase the pressure by 20 PSI, boiler runs normal. But that is the difference between knowing the numbers. Everything in a steam system happens because of physics and the numbers. But don't get discouraged because you are not an engineer and you can't crunch numbers. You just have to, at a starting sense, you have to understand in general what happens when you increase steam pressure, decrease steam pressure, and the properties of steam. I would always recommend having access to or knowing the properties of saturated steam chart. It's something good to have, something good to reference. And a lot of times customers will ask you, hey, like if we want, this steam pressure here at this process, do we really have to run this pressure? And you go, well, this pressure, say the customer says, hey, we want 300 degrees at our process. Do we really have to run 110 PSI? And you go, well, 110 PSI is 344 degrees Fahrenheit, and 60 PSI is actually 307 degrees. So you could run 57, 56 PSI steam and get around 300 degrees. So you don't have to actually run 110. So you can lower that if you only want 300 degrees of steam. But then you have to also look at the size of your piping and your velocities of your steam, because that comes in and plays with it. But hopefully tied that together correctly. If I said something wrong, I want to know. I want to learn. DM me on LinkedIn. Email me, eric.johnson@boilerin.com. If you want to be a guest or have guest recommendations, you can email me or DM me on LinkedIn. Working on that, trying to provide value other than me rambling on this podcast, but want to grow and educate the boiler industry. It's a great industry, lots of opportunity, especially with AI taking away traditional jobs. But hopefully you got something, you learned something out of this. Go look up a steam table, saturated steam table. If you haven't already or don't know what they are, go look at the numbers, and steam won't be a mystery anymore once you start looking at that. That is the physics behind steam and why the temperature versus pressure relationship of steam is. So I thank you for listening. If you've gotten this far, please rate the podcast 5 stars. That really helps me out. I hope you have a great day and stay wild.